In this video, we use Abaqus to model a plate with a hole as shown in this figure. The plate is subjected to a tensile load of 25 megapascal. Its material is a steel with a Young's modulus of 200 gigapascal and Poisson's ratio of 0.3. We model this plate as a two-dimensional plane stress model. Now, because the plate has two axes of symmetry, we can take advantage of the symmetry to reduce the size of the model, and we can model basically only 1/4 of the domain as shown in this figure here. Symmetry boundary conditions should be applied on the symmetry lines. For this purpose, we prevent the domain from moving perpendicular to the symmetry lines by applying rollers on the symmetry lines. Now let's go to Abaqus. We start by creating a part, and I call it a plate. It's a two-dimensional part, and the approximate size is, I use 800 because I'm using millimeter as the unit for the length. As a unit for length, we are using millimeter, and for force, I'm going to use Newton here. So I first create the entire domain, the entire plate. Let's apply dimensions to this. This is 250 millimeter, and this is 100 millimeter. And we need to define a hole in there. The radius of the hole is 10 millimeter, and the hole should be at the center of the plate. So the distance between the center of the hole and the edge of the plate is 50, which is correct here, and the distance between the center and the top edge should be 125. All right, now we have the plate, the entire plate and the hole. What I'm going to do, I'm going to partition this. Creating lines that go through the center. All right, and now I can trim it, trim the edges that I don't need. And this is 1/4 of the plate that we want to have as the model. Alright. After defining the part, we go to property to define the material properties. Our material is steel, and we model this as an elastic material. Because I'm using Newton and millimeter for the units of force and length, the Young's modulus, the unit of Young's modulus is megapascal, and 200 gigapascal is 200 E3 megapascal, and Poisson's ratio is 0.3. We need to create a section. It's a plate section. It's solid, homogeneous, and material is steel. The domain is plane stress with a thickness of 0.5 centimeter, which is 5 millimeter. After defining the section, we should assign the section, and we assign the section to entire model. Done. And the only section we have defined is plate section, and done. So we have created a material and assigned it to our our part. Now we create an instance of the part in the assembly. I create a dependent instance. And we define a static step for our analysis. All the default values are good. And we go to load. We apply the boundary conditions first. So roller, I call this roller 1, and apply the boundary condition to this edge by fixing the displacement in the x direction. We repeat the same thing for the bottom edge, call it roller 2, and this time I fix the boundary, I fix the displacements in the y direction. And we should apply a force also, the tractions of 25 megapascal to the top edge. We apply it as pressure, and the loading is applied to the top edge, done, and its magnitude is -25 because it's tensile. Okay, so we have applied all the boundary conditions. Now we need to mesh this. To mesh this, what we are going to do, we are going to have a finer mesh close to the hole, because we know we have a stress concentration around the hole and we want a higher accuracy or a finer mesh in order to be able to capture the stress concentration that is occurring around the hole. So we see the edges, because the model is, the instance is dependent, I have to mesh the part. So we see the edges, and let's first see this edge, done. And for the bias I choose single, and I go by number here, and I want, let's say I want 10 elements on this edge. Now the arrow direction here shows the direction of the refinement, so this shows that our mesh is going to be finer close to the hole. And okay, so we see that we have finer mesh here. We repeat the same thing for the other edge here. Again by number. For this one I used, it's a longer edge, so I choose 20 single bias, but this time the arrow is in the wrong direction. We want to have finer mesh here, so the direction, we need to flip the direction of the arrow. All right, okay, the last part is to mesh the hole, and for this one I go without bias, and I go with 20 seats around the hole. All right, let's mesh this, and before I mesh it we need to define what kind of element we want. Our element is plane stress. I'm going with linear elements, so it's good. And then the shape of the elements, we can choose between quad, triangular, or quad dominated, which basically means that the domain tries to the Abaqus is going to try to mesh the domain with quad elements, but if it has to use triangular elements also, it's going to use them. So for this one, let's try triangular elements for now, and we select OK. Now we mesh it. So you can see that this is the mesh that is generated. We have finer mesh around the hole here. Alright, so After this, we can go to job and create a job. And we can submit the job. So this should take a couple of seconds, a few seconds before it completes. Alright, so the job is completed. Now we can look at the results. So similar to before, you can look at the stresses. You can look at the Mises stress, or you can look at the stresses in the X direction. You can see that we have a stress concentration around the hole as we expected. We can look at the stress in the Y. We can look at the shear. I'm sorry, stress in the Z, and look at the shear here. This is the shear stress S12. And we can look at the principal stresses. Also, you can have the deformations if you want. You can look at the deformations, magnitude, or the components, or the reactions. And you can create reports if you want to, using the report option here, and choose the field output that you want to create a report for, as we talked about them in the previous videos. Alright, thank you for watching this video.